just forget to record. Okay, so, and what is true about oscillating systems is the following. You need two forms of energies, okay? And energy oscillates, energy is being converted from one form to another. And as long as there's no friction or there's no dissipation of energy, the total mechanical energy will be constant, okay? If there is friction, what happens is this energy is converted to heat, and heat energy just spreads away, okay? So as long as there is no dissipation of energy, energy is being converted from one form to another in an oscillating system. In this case, it's being converted from kinetic to potential energy, okay? Now, on this mass, you can see that it's going the fastest at the center. When it's going to the right, its velocity is positive. When it's going to the left, its velocity is negative. It's going fastest at the center. It's at the end points, it's at rest. Now, if you look at the force vector, the force on the mass is the greatest at the end points, meaning the acceleration of the mass is the greatest at the end points, okay? So the velocity is maximum at the middle, in the middle, and the acceleration is greatest at the end points. All right, so this is the system we want to study. You start at one end, okay, and go there and come back. That's one oscillation, okay? And the time for one oscillation is called the period of the oscillation, okay? So we'll encounter all those terms. All right, so this is the system we are interested in studying, okay? All right, so let's get started with the slides now that you've seen that. All right, so the motion of this mass is a simple harmonic motion, and the reason it's called a simple harmonic motion is because its position can be expressed in terms of a sine or a cosine function. Okay. We'll look at the energy in the simple harmonic motion. We'll see a lot of examples of simple harmonic motions. So this is the typical example, but you'll be amazed at how many other motions mimic this motion or are described by the same equations. We'll look at simple pendulum, and we'll see how this motion is related to an object going in a circle at constant speed. It turns out that this motion is related to uniform circular motion. And then we'll look at forced oscillations and resonance. Okay. All right, so a periodic motion in general is any motion that repeats regularly. Yeah. Now, this is a special kind of periodic motion. And like I said, we call this a simple harmonic motion. And the feature about this is that the restoring force, when you disturb, so this is the equilibrium position of the system. When you disturb it from the equilibrium position, this is the restoring force. See, here's the restoring force. This force wants to bring the system back to its equilibrium position. The restoring force is proportional to the displacement, okay? And this is Hooke's law, and that's the spring constant. Yeah, so we saw that before, yeah. Now, here's a very important slide. Okay, so this will sort of give you a preview of why you do differential equations. Now, as I said, we are interested in learning the behavior of this system. Yeah. Now, there's two ways of doing this. You can set up an experiment and make observations and all kinds of stuff and make measurements. And generally, doing an experiment is hard. So one could do that. Okay. Now here's an alternative. What we'd like to do is build a mathematical model describing the behavior of this system. Okay. So we want to set up a mathematical model. And generally a mathematical model describing the behavior of a physical system is a differential equation. Okay. So that's why you'll study differential equations. So this equation describes the behavior of the system. Okay, so I'll show you how to set up this differential equation. And so this differential equation describes the behavior of this system. And you can solve this differential equation. That's easy. Okay. And here's the solution to that differential equation. What x is the x is the position of this mass. And to understand, well, what you're interested really in is the position as a function of mass, as a function of time for this mass. Okay, guys, I like to pause a second. My dog is barking and I like to bring him in. Okay, I'm sorry about this, but I'll be back in a second.